Okay, so first of all, thanks a lot to the organizers for a really nice meeting. It is very challenging to organize such a virtual meeting, and I think it's going super well, even though I have the complaint of the schedule. I don't like waking up this early. And I take the chance to make this joke because since Jean-Philippe did such a nice introduction today, I can go very quickly through my introduction. So basically, this development that we are doing in Valparaiso to try to get cheaper primary mirrors for telescopes, which basically will translate into much cheaper telescopes, is fully motivated by the planet formation imager. So basically, we have seen through this week uh, wonderful results with high angular resolution, like for example, the discovery of PDS-7TV was talked since the very first talk by Cora. This protoplanet, um, well, it's basically the dream for many of us, right? But it still is a point source, right? We cannot resolve it. And it is still relatively far away from the star, where we know that there are not so many planets. So we want to go closer to the star, and we want to be able to resolve these things to understand much better how they form. So basically, this is the motivation for PFI. So if we jump from the 8-meter class telescopes to the giant and extremely large telescopes, we will be getting a factor 5 in resolution, a factor 25 in area. To be able to resolve these objects, we need to go much farther. So, and we don't need such a big field of view, right? This PFI definitely won't be a survey machine. It will be a very specialized object by object machine. So the concept of PFI is to have a kilometer base mid-infrared interferometer that will allow us to have this exquisite, ridiculous resolution that will allow us to see the Hill sphere of a proto-Jupiter while forming in a typical, relatively typical star forming region. We will go to 200 parsecs. We were doing target selection for 400 parsecs even. And of course, this project is extremely ambitious and has plenty of challenges. Um, there are some very complicated that Jean-Philippe put a very super nice context this morning that are related to whether it is going to be direct interferometry or heterodyne interferometry. But there is, regardless which road we go, there is the problem of the telescopes, right? If we want to do image reconstruction, if we want to really take advantage of this resolution and have as realistic images as possible, we need to change probably the way we do telescopes because we need many. We need more than 10. We need hopefully between 20 and 30. And the way we make telescopes nowadays is a problem in terms of time cost and in terms of actual like money cost. So in Valparaiso, we set ourselves the pretty ambitious goal to tackle this problem and see how we can change the cost of the telescope. So as we all know, the cost of the telescope is directly driven by the primary diameter, and that is very much driven by the weight of the primary. We know that there has been huge advantages, even for a long time now, with being able to do active optics, for example, we can lower the weight quite a bit, but still glass is heavy. So what we are doing in Valparaiso is we are trying to use different materials that will allow us not only to go lower in weight, but also to serialize the process of making one of these mirrors. So how this starts is we are going to serialize. So basically the easiest way to serialize is just to copy something, right? We don't make unique things. We just make one unique thing and then we copy it. So that thing that we are going to copy is what we call our mandrel. So our mandrel is a piece of material of the same roughness surface that we need and the complementary shape. So basically, if we want a concave mirror, spherical concave mirror, we will have to make a convex one. We have been playing with many different materials that have offered different properties in terms of hardness, in terms of how we can polish them, to which degree. And we are now working mostly with different kinds of glass, but we are also producing some experimental ceramic glass on our side. And we reach surface roughness between 10 and 20 nanometers for the surface. And we've been working with flat surfaces also for calibration purposes, but mostly with the spherical things with a short f. Um, so once we have our mandrel with the quality that we need, then we have to figure out the material that we're going to use to replicate that mandrel to get the complementary shape. So the material that we're using is carbon fiber reinforced polymers, sorry. And why are we using carbon fiber? Well, we are using a composite material because if you can see here, I hope it's large enough, I'm showing a diagram where you have the density versus the strength of different kinds of materials. So composites are up here in the purple bubble. And the kind of composites that we are using are carbon fiber based. So basically they are reinforced with carbon fiber. And then you have some kind of epoxy, some kind of resin in which this material is being held together. So basically the way this works is you have a mandrel that has the properties that you need. And then you use different layers of this material to copy the shape. And I will go in a second how you copy the shape. Thank you. So in order to have the most reliable copy that we can, we need to work with different kinds of composite materials. We need to understand how many layers we need, the orientation. There is a lot to play between quote unquote with this material. So I'm gonna go a bit faster. These materials, once you have made your layup on top of your mandrel, ideally you want to go to very high pressure and very high temperatures with the very good control of those both quantities. Right now we are working just with quotes in an oven with vacuum, but still that is working well enough to have replicas, relatively small replicas. So we have been building 20 centimeters. Now we're working on a 50 centimeter replica. Replica, I mean a carbon fiber mirror. And we are in the process of acquiring, well, in fact, it is being shipped, an autoclave that will allow us to go to much higher sizes. So once you've baked your replica, now you have basically reflecting carbon fiber mirror, but you want to make it a lot more efficient. So you want to coat it the same way you coat glass. So we've been using sputtering that gives really good results. And we have a sputtering machine with 2 channels. So we can be depositing, well, bombarding our mirrors with aluminum, for example, but at the same time with some kind of hardening and protective layer like SEIO, for example. We're doing that with 20 centimeters. We already have a chamber that is almost ready for 60 centimeters. That's an evaporation one, not a sputtering. And we have a 2-meter sputtering chamber that is being refurnished. So what kind of precision are we achieving? So we measure at all different of space frequencies. So basically we measure waviness, we measure roughness. And so far for 20 centimeters, again, this is small mirrors, but bear in mind that we've been working on this for less than 3 years and we started with basically nothing. So for 20 centimeter mirrors, we are getting roughness consistently of below 20 nanometers and waviness below 100 nanometers. And this is pretty dominated by the fact that we are still not using autoclaves. So this should improve a lot. Also, while we are growing in size of the mandrels, we also need to characterize the mandrel, not only the replicas. And characterizing convex figures is a very fun game. So we are exploring how to do deflectometry properly to have a really precise characterization of our mandrels or our big mandrels. Does this really make sense? Are we really fulfilling our promise of getting something cheaper? Well, we all know this classical figure of how the cost of the telescope scales with the cost with the aperture of the telescope. And again, this is dominated by the primary. So if we scale down to 20 centimeters, which I know we cannot do, but this is what we can do right now. This is the thing that we have to compare. A 20 centimeter replica ready to go, which includes absolutely everything. And of course, it's overestimated because we got a lot of equipment that is included here. And we are assuming that we can do very few, and very few, I mean only 40 copies per mandrel, which we know that we can go much higher. 20 centimeter replica will go for less than $450 US. Amount for such a lightweight gets much cheaper because it's really light. It's basically 200 grams versus 2 kilos.
Try to conclude.
Yes, this is my final slide. We'll go for below $750 US. So basically this is less than 2/3 the cost of a 20-centimeter telescope in the market right now. So, and also it takes less than 2 days to make the mirror, which is also huge compared with a classical glass mirror. So yeah, I hope I've convinced you that we are progressing in Valparaiso and that this is a really exciting avenue. And I will take questions if there is time. I'm sorry that I went overboard a bit.
There is one question. I mean, for me, it's okay, Leo, you cut when you think it has to be cut. Can this mirror be recoated, and how does it behave with time?
That is awesome because that gives me more time to speak. So they can be recoated. So there was a body of literature that said that the chemicals that you use to recoat, so basically you have to get rid of the previous coating and then recoat, will damage the fiber. And we were acting on those premises, but like around a year ago, we were in the situation where we needed to recoat. We didn't care if the quality was going to be good or not because we were testing something else. And we recoated a couple of mirrors, and the roughness, surface, everything, nothing deteriorated. There was really no change, so they can be recoated. And the question on how long they last and how long they will have to be recoated, we have some abandoned prototypes in Paranal. ISO was super nice to let us bring some of the originary prototypes that were not astronomy roughness surface characteristics yet, but we could coat some things and send them to the mountain. They've been there for months. We are hoping that once restrictions stop, we could go and recover them and have a better idea on the deterioration of the reflectivity.